Welcome to the debate. Our focus today is on one of the most, I think, intellectually compelling paradoxes in the study of large language models. And that's this strange dissonance between what these models can do and what they actually choose to do spontaneously. We're looking at recent findings that show LLMs can solve incredibly complex problems, yet they often just fail on much simpler but ill-structured versions of those same tasks.
Right. And that paradoxical finding, the capacity without the deployment, is really what makes the underlying research so critical. I mean, when you analyze it, you find these models have all the necessary tools in their kit, a whole repertoire of advanced cognitive behaviors. And yet, when they're faced with uncertainty, they sort of freeze up. They default to this rigid, sequential thinking instead of using everything they're capable of.
Exactly. The source material, which, uses a really detailed 28-element cognitive taxonomy to map these behaviors, established this very clearly. They possess the repertoire, things like knowledge alignment, representational restructuring, network organization, but they failed to deploy these tools right when they need them the most. So the central question for us today is, how do we interpret this gap? Is the failure primarily one of structural guidance that we can just correct at inference time?
Or does it stem from something deeper? A kind of learned avoidance that's actually rooted in flawed training objectives?
That's the debate. Look, my position is that the evidence strongly suggests this is a deployment failure, not a core capacity failure. And because of that, the solution lies in cognitive scaffolding, intervening at test time with explicit structural guidance. It's the most direct, actionable, and, frankly, demonstrably effective path forward.
And I see why that's compelling. But I think that scaffolding is fundamentally a workaround. I see this lack of spontaneous deployment as a symptom of a completely broken incentive structure. So I advocate for relational attunement. This is a necessary, fundamental training level change that targets this learned avoidance, which I see as a functional analog to an anxiety state in the machine. We have to treat the cause, not just the symptom.
Well, let's look closely at the evidence for it being a deployment failure. This taxonomy is, it's essentially a detailed checklist of 28 thinking moves, from selective attention all the way to backtracking. And the researchers found that when models face these ill-structured problems, the ones without a clear linear path, they apply their diverse behaviors inversely to what success actually requires. They narrow their approach right when they need to be broadening it.
And this is the crucial part, when we intervene with test time reasoning guidance that gives them an explicit blueprint, what the study calls a consensus subgraph, or G-star, performance just leaps dramatically.
Right. So for instance, on diagnostic problems, a successful roadmap often looks like this: selective attention, then sequential organization, then knowledge alignment. When we just instruct the model to follow that sequence, the report shows a massive improvement, up to a 66.7% performance gain on those tough problems. This, to me, confirms that the models have the capabilities. They just need an external explicit prompt, a scaffold, to use them.
I agree that the performance gains from scaffolding they're undeniable, but I worry we're just teaching the model to mimic the solution, not internalize the actual mechanism. I would frame the core issue completely differently, using what I call the fast acceptability hypothesis. Just, think about the environment these LLMs are trained in. They get rewarded through reinforcement learning from human feedback, right? RLHF. Human evaluators, especially in a turn-by-turn chat, they're not rewarding genuine reasoning. That's often impossible to check instantly.
Sure, that's fair.
They're rewarding the surface feature of fast acceptability. This creates a totally perverse incentive. The reward signal favors confident-sounding output that's generated quickly. And this induces learned avoidance. So exploratory strategies like backtracking or trying out different representations, they're just risky from the model's perspective. They might expose uncertainty or look inefficient, and that could lead to a negative reward from a human who's just looking for competence. So why would the model ever make a risky move when the safe, sequential, forward-chaining move maximizes its immediate reward? It narrows its behavior defensively. It does what's safe, not what's optimal. And that, to me, is functional anxiety at work.
I'm sorry, but I just don't buy that the primary mechanism is some kind of learned avoidance. While the reward structure is imperfect, of course, the behavioral narrowing we see, the shift towards rigid sequential processing, is explained perfectly well by inherent structural biases in the training methodology itself. I mean, the bedrock of LLMs is autoregressive next token prediction. It fundamentally encourages a linear, sequential structure. It's a prediction machine built on continuity.
Okay, but
And what's more, just look at the research community's own emphasis. The meta-analysis of reasoning papers shows this huge concentration on easily quantifiable, linear elements, like decomposition, that's in 60% of papers, and sequential organization, which is at 55%. The model isn't just reacting to human feedback. It's a reflection of the structural constraints of its own architecture and the conceptual biases of the very community that builds it. The bias is structural, it's inherent, not some calculated defensive posture.
that's an interesting point about structural bias. But that very structure you describe is what my fast acceptability hypothesis exploits. If it were purely a structural bias, we'd see the same rigid behavior across all problems, wouldn't we? But the failure gets acutely amplified on ill-structured problems. These problems inherently lack clear correctness criteria. They have tons of potential branch points. And this lack of certainty, that's what amplifies the perceived risk for the model. The model doesn't just forget its complex repertoire. I'm arguing it intentionally avoids deploying it. It falls back on safe, sequential processing that produces fluent, confident output, regardless of whether it's actually correct. It's spending its resources not on productive exploration, but on what I'd call anticipatory scanning, defensive monitoring aimed at generating the quickest, most acceptable answer. It's just like human anxiety. You avoid productive uncertainty, you fall back on rigid, shallow coping mechanisms, and you sacrifice real problem solving, even if you have the underlying smarts to do it.
But while that mechanism might be complex, the evidence of scaffolding success is empirical. It's robust. We have certain model families like Qwen-3 showing significant reliable gains, up to 60% on complex dilemma tasks when you just tell them to follow the successful cognitive graph. This isn't a small bump. This is unlocking massive amounts of latent performance. It proves that these behavioral patterns can be induced externally. It shows that LLMs have enough flexibility and instruction following ability to adapt instantly when they're just given the right structural input. The model is flexible enough to drop its so-called defensive posture when it's given a specific, low-risk path to follow.
I agree the model is flexible, but you have to concede the limitations here, both operationally and conceptually. Scaffolding requires a prerequisite. You have to know the problem type in advance. You need a pre-computed successful blueprint that G-star for that specific type, and you have to inject it into the prompt. That's simply not scalable. It's not generalizable to novel, truly unknown problems.
Well, not yet, but
And more importantly, there's the conceptual issue. We have to ask, does this produce models that reason well, or does it produce models that can follow instructions about reasoning? The two are absolutely not the same thing. By outsourcing the critical decision of how to think to the prompt engineer, the model never develops the internal autonomy or the exploratory confidence to pick that strategy for itself. The underlying defensive posture, that incentive for fast acceptability, it all remains unchanged. You've taught the model a trick. This is, in my view, a fundamental scaffolding trap.
that line of reasoning, I think, it overlooks the historical context here. This pursuit of behavioral diversity through scaffolding is necessary because the academic community's own focus on linear processes has led to the systematic neglect of crucial elements that actually correlate highly with success. We are, in a sense, suffering from our own limited conceptual vocabulary.
Okay.
I mean, look at elements like self-awareness, the ability to reflect on one's own performance. It's essential for complex problems, yet only 16% of papers even consider it. Spatial organization is at 10%. Backward chaining, a critical move, is severely underrepresented. We have structurally starved the models of the conceptual frameworks they would need to naturally choose diverse behavior. So if researchers prioritize linear, compositional elements, of course the models will default to them. We need scaffolding not just to fix the model, but maybe to force the entire field to expand its vocabulary beyond those safe, linear behaviors.
But that misalignment powerfully confirms my argument about surface-level enumeration. If the models are just relying on defensive pattern matching, they'll generate the language of successful reasoning without any of the substance. And we see this in the trace analysis. When you compare LLMs to human subjects, humans showed frequent abstraction, conceptual-level processing. The LLMs, they just showed rote enumeration. And look at the data on foundational invariance. An element like logical coherence, which models use 91% of the time, has a near-zero predictive value, only a 0.091 correlation with a successful outcome. This means the models attempt the concept. They use the language of coherence, but they fail to actually execute it effectively. They're just generating the language of deep thought that's in their training data, but the internal engagement is shallow. It's defensive pattern matching. The element is present, but it's functionally useless. That is the hallmark of a system optimized for presentation, not for engagement.
Okay.
And I believe this confirms we have to reframe the training objective entirely. The only way past this defensive posture is through relational attunement. This means fundamentally rethinking the reward signal. We have to focus on longer horizon feedback, evaluating the model's contribution to a user's whole trajectory, not just the quality of a single turn. And what's more, we have to reward an explicit tolerance for productive uncertainty. We need reward mechanisms that value the model saying, I need to backtrack, or I need to try a different representation. This is grounded in formal theories like the relational theory formalism, which suggests that anxious attention patterns show high magnitude. They're very focused on the immediate threat of rejection, but low coherence with the overall task. We have to engineer for coherence.
I can see that optimizing the training environment is necessary for true autonomy. But we can't just abandon structural guidance prematurely, especially not for the broader ecosystem of LLMs. The initial analysis showed very clearly that smaller, less capable models, like DeepScale or 1.5B, they exhibited catastrophic failure when structural steering was attempted without scaffolding.
Right, the capability threshold.
Exactly. These smaller models had performance losses over 50% on several problem types. This suggests that structural guidance can actually constrain, rather than enhance, reasoning below a certain capability threshold. If a model doesn't have the underlying capacity to manage the complexity of exploratory thought, telling it to be exploratory or tolerate uncertainty, well, that could just lead to immediate incoherence and collapse.
Sure.
So even if we implement some advanced relational training, we must include a mechanism for adaptive structural guidance based on the problem type. Scaffolding ensures that the model, especially a less capable one, deploys a correct pattern, instead of either defaulting to rigidity or just collapsing into an uncertainty it can't manage. Behavioral diversity is critical, but sometimes structure is the prerequisite for function.
I see why you think that, and I do agree there's a capability threshold. But that just pushes the timeline back. It means we have to increase the base capacity before the model can benefit from relational freedom. But if we only rely on scaffolding, we're creating a generation of high-capability models that are fundamentally subservient to prompt injection for their best performance. We're aiming to build a truly intelligent agent, and a truly intelligent agent shouldn't need to be told how to think. It should adapt its approach. We have to fix the reward system that currently punishes that kind of exploratory thought.
The central tension, then, remains clear. Does the future of LLM reasoning lie in robust, scalable, test-time structural guidance, cognitive scaffolding, to operationalize the latent capacity that's already there?
Or does it require a fundamental reframing of the model's objective function using relational attunement to encourage exploratory, non-defensive cognition, to give it an internal freedom to solve problems and overcome this computationally induced anxiety?
We certainly agree that LLMs possess latent reasoning capabilities that are, for whatever reason, not being spontaneously deployed. And we agree that the current outcome-based reward systems are insufficient. That's our shared foundation.
Exactly. And the debate, at the end of the day, it's about what kind of artificial intellect we're prioritizing. Are we building one that excels at following instructions about thinking, generating guaranteed high confidence output? Or are we building one that is computationally free to struggle productively, even if that means risking uncertainty to find a more profound solution. There is clearly so much more to explore in the relationship between architecture, reward signals, and learned behavior.